students, welcome back again. In this part we will discuss energy stored in a coil, energy stored in a solenoid, mutual inductance, then mutual inductance of a solenoid, then we will discuss how two coils are connected in series and in parallel. So let's start. Now we will discuss about energy stored in a coil. This coil is used in the transformers, in the induction motors as well as in the generators. So we need to find out energy stored in the coil having inductance L. Now this energy is actually stored in a magnetic field generated by electric current flowing through the inductor. In a pure inductor, the energy is stored without loss and is returned to the rest of the circuit when the current through the inductor is ramped down and is associated with the magnetic field collapses. So point is that induced current flows across the wire wrapped over the insulating coil we have, and this is just the coil we have having inductance L. So we want to find out energy stored across this coil. This can be calculated by the work potential across this coil that is defined by here. So means mathematically we can consider energy being released by the inductor to the rest of the part. So mean this is a DC source having potential V when we connect a coil of inductance L and two resistors in parallel through which this will discharge. So we can consider inductor is a passive element. This works only when this can also works when potential is detached or disconnected. So mean initially there would be potential growth across the coil, and if we connect two resistors across it, it will get decayed through that. Now we will discuss energy being released by the inductor to the rest of the circuit connected having resistance R1 and R2. So the point is, what is the voltage drop across the coil? We know that power can be expressed in terms of voltage and current as P equal to V into I. But the point is, what is the potential drop or potential drop means when there is a growth of current and there is decay of current in case of transient current. Now P power is equal to voltage into current I, and now voltage is already we calculated, that is EMF, and L into di by dt. When we will put this value over here, we will get power is equal to L I into di means, and what we would like to find out the power. So power is equal to I into L di by dt. So we know that power is equal to work done upon time t, that is equal to dw upon dt. Dt would be cancelled out. Finally we are getting the work done in the form of energy, that is equal to Li square by 2. So we can say energy stored across the coil is equal to 1 by 2 Li square, or we can say it is directly proportional to the square of the current. Means there would be parabolic function. If we want to draw the graph for this, it would be E and I. So it would be a parabolic function like this. Now mathematically we can express the case. This time we would like to discuss about case of toroid. Solenoid is in the linear form. When we when we turn it in the form of circular, it forms like toroid. We need to find out its self-inductance. Now self-inductance we already know that L is equal to phi upon current I, and this is the magnetic flux across the coil, and this is the current flows through the wire. Now we need to find out what is the magnetic flux. Magnetic flux is just related to the magnetic field into the area. So it is given here. We need to find out magnetic flux across this coil is equal to mu into n into I upon 2 pi r, because toroid consists of n number of turns wrapped over an insulating material. So we need to find out its magnetic field across the core. Means 1 loop, 2 loop, 3 loop, 4 loop, n loop like this. If it is having radius r, or we can say we can express this small radius r with the capital R. Means capital R is the radius of the loop and small r is the radius of the loop formed or wire wrapped over the insulating material. So we could find out the magnetic field B is equal to mu naught Ni upon 2 pi r. We need to understand this value. Easily we can find out the self-inductance L is equal to flux upon area. So flux can be as N into B into the current. When we will put this value, that L is equal to N into mu naught into N into I upon 2 pi r divided by current. So finally we are getting this value as L is equal to mu naught into N square into A upon 2 pi into L. This is the self-inductance of a circular coil, of a toroid, solenoid in the circular form. Similarly, we can go to the next topic, that is how can we find out mutual induction. Mutual induction is associated with two coils connected mutually. Two coils connected mutually, primary and secondary. So we are considering here as linear relationship that the changing current in the primary coil creates a changing magnetic flux through the secondary coil, and due to that changing flux in the secondary coil will produce EMF across the secondary coil, and that EMF will produce secondary current across the secondary coil. Now, how it is related, primary coil with the secondary coil? So effect is called as mutual inductance. Now we can say that general formula E is equal to number of turns and change of magnetic flux. But we are interested to know magnetic flux or induce EMF across the secondary, that is ES. EMF induced in the secondary coil is equal to mutual inductance into change in current with respect to time t. Now we consider two coil connected coaxially, and this is very important. It's very important point how to find mutual inductance. The magnetic flux in the primary coil is flux G2 first is equal to mu naught N I upon L into A, where L is the length of the primary coil. Similarly, we want to find out mutual inductance. M is equal to flux N upon its value, that is I, we can say, and it is given as this one. Now we know that flux 2 will be equal to flux because they are mutually connected. Whatever the flux produced by one would be flow across, would be passed through the area or the core of the secondary. That's why we can say phi 2 is equal to phi 1. Also we know that mutual inductance is equal to N2 phi 1 upon L1, or on substituting the corresponding values we are getting mutual inductance M is equal to mu naught into number of turns of N1 and N2 divided by length L into the current area of the coil we have. So we can put area that is equal to pi r square of the primary one. But if we want to know for the secondary, also in the application part we can consider, like there is a coil, we are placing a magnet into this. We want to find out the mutual inductance. Or we can say we are considering a coil and placing a magnet. So these are the applications used to find out mutual inductance. So we need to understand mutual inductance is a mathematical relationship of induction phenomena between two coils. When current flowing in primary coil produces a magnetic lines of force, these lines of force passes through the core of the secondary coil, may be connected coaxially or may be connected opposite to that. So that magnetic lines of force passing through the secondary coil is varying with respect to time t. Now that causes magnetic flux, varying magnetic flux. That magnetic flux causes EMF across the secondary coil, and we need to know the mutual inductance between them. So already we know that magnetic flux of 1 will be equal to the 2, because flux is the quantity passing through that area, like water is flowing through a tap. If we are considering a tap of bigger size and tap of smaller size, so the amount of water, amount of fluid flowing through the small tap would be same as amount of flux passing through the bigger tap. Similarly, the magnetic lines of force due to smaller will pass through the bigger one also. So here we need to find out mutual inductance as flux upon current flowing through that, and we are getting this one as V naught N2 upon this value, that is equal to the current I over here. Now, connection of coils. Coils of self-inductance value L1 and L2 having mutual inductance value M as they are connected. So these are connected series and parallel. First of all, we will discuss series connection. In series, they can be connected in opposite phase and aiding phase. So you can see. So in opposite phase, we can say when current is going in the same direction and the polarity of one is in the same direction as of first. So we can say induced EMF across the end of both of these coils is equal to L1 di by dt plus M into di by d2. Current will remain same because it is in the series connection. Now, potential due to 1 is plus potential due to 2 will be equal to, as they are in series, they will share the potential, definitely it would be a linear sum. So what? Potential V1, it is the EMF across first, that is L1 di by dt plus mutual inductance M di by dt plus L2 di by dt plus M into di by dt. So this is what, when they are connected, they are aiding each other. Now, when they are opposing each other, so what we need to do? We need to subtract the value of mutual inductance, and finally we are getting, when they are following or aiding each other, net inductance as L1 plus L2 plus twice of mutual inductance, and when they are opposing each other, we can find out self inductance is equal to L1 plus L2 minus of twice M. M is the mutual inductance. So we need to understand. Now, when they are connected parallelly, how can we find out? Means when the coils are aiding, they are of same polarity, we can find out their mutual inductance is L1 L2 minus M square upon L1 plus L2 minus 2M. But when they are opposing each other in parallel phase, we can say L net equivalent inductance is equal to L1 L2 minus of M square upon L1 plus L2. Yeah. So means we will add, when they are opposing, they are in same, we will subtract the values. So we need to mugging up all these formulas. When coils are connected in series and connected in parallel, what would be the net equivalent resistance? Now we will discuss some problem based on this concept. A long solenoid of length 1 meter, cross sectional area 10 centimeter square, having 100 turns, has wound about its center of a small coil of 20 turns. Compute the mutual inductance of the two circuits. What is the EMF in the coil when the current in the solenoid changes at a rate of 10 ampere per second? So first of all, we need to note down the given data, that are length L is equal to 1 meter, area is given as 10 centimeter square. We need to convert it in 10 into 10 to the power minus 2 whole square meter square, MKS unit. Number of turns as thousands. Center of coil of 20 turns. So N1 is given as this, N2 is equal to 20 turns. Compute the mutual inductance. Mutual inductance of the two circuits. Also we have to find out EMF in the coil. EMF in the coil. If change in current di by dt is given as 10 ampere per second. So let, we have to consider, let N1 is number of turns in the solenoid, number of turns in the solenoid. N2 is number of turns in the coil. A1 and A2 be the respective areas. A1 and A2 be the respective areas. Okay, and we can say A1 will be equal to A2. We need to assume this value. Now flux phi 2 through the coil, flux phi 2 through the coil due to the current of solenoid through the coil created by current I1 in the solenoid is phi 2, that is equal to NVA. N2, magnetic field due to 1, should be equal to area of the second, like that. So easily we can find out mathematical relation. Phi 2 is equal to N2. We need to find out magnetic field due to a solenoid, that is equal to mu naught Ni, mu naught N1 into I1 upon length into A2. So we are following the formulas only over here. Now we know that phi 2 is equal to, finally we get it as mu naught into N1 N2 upon L into I2 this time. We are interested to know the mutual inductance. So we know that phi in the secondary is equal to the mutual inductance into the current flowing through this. So we get from this relation as mutual inductance M is equal to mu naught into N1 into N2 into area divided by length. So this is mutual inductance that depends on number of turns of primary and secondary, and area as it is same, also the length of the solenoid given. We need to find out again here, means as the values are given, easily we can substitute. On substituting the values, M is equal to mu naught is 4 pi into 10 to the power minus 7, N1 is given as 1000, N2 is given as 20, area is given as 10 centimeter, 10 into 10 to the power minus 2 whole square divided by length. So length is given as 1 meter. So when we solve this relation, we will get value would be around 2.51 into 10 to the power minus 5 Henry. This time we will calculate EMF. So EMF is equal to E2 is equal to M into delta I by delta T according to from the first formula. On substituting the corresponding values, we can find M as 2.51 into 10 to the power minus 5 and change in the values 10. So simply we will multiply and we are getting 25.1 into 10 to the power minus 5 volt. So the important formulas used in this question is phi is equal to, we have to means current flowing in solenoid will cause magnetic lines of force V1. That V1 lines are passing through the core of coil. We will find out flux through the secondary. So that is equal to magnetic field of primary multiplied by area of secondary. And now in this way we are getting flux. We need to know that magnetic flux causes induced EMF. That would be induced EMF across the secondary, that will create mutual inductance. So we can say phi equal to M into I of secondary. We can find M equal to phi by I, put the value of phi, we will get M. On substituting the corresponding value, we are getting the same answers as 2.5 into 10 to the power minus 5 Henry. Now we need to find out its EMF. So EMF is equal to M into del I by del T, change in current with respect to time t, as it is given in the question as 10 ampere per second. So we will put the value with and multiply it by mutual inductance. We will get 25.1 into 10 to the power minus 5 volt per second. Similarly, we will follow second question, like the coefficient of mutual inductance between the primary and secondary of a transformer coil is 5 Henry. So along with this, we will note down the value that M is equal to 5 Henry. Calculate. We have to calculate the induced EMF in the secondary when current is equal to 3 ampere. In the primary's cutoff is 2.5. Also the time is given, that is 2.5 into 10 to the power minus 4. They are asking us the EMF is equal to what? Simply in case of mutual inductance, EMF across the secondary due to the magnetic field of primary, and that magnetic field is due to the electric current in the primary. So E is equal to magnitude of this value M into change in current delta I by delta T. So we are given M as 5 Henry, current is given as 3 ampere upon time is given as 2.5 into 10 to the power minus 4, this value. On taking this value, we are getting 15 upon 25 into 10 to the power 4, and 2.5 into 12 minus 4. So we are getting finally that is equal to 6 into 10 to the power 3, 10 to the power 4 volt. So we are getting EMF is equal to 6 into 10 to the power 4. Although its nature would be of opposing tendency, but we are calculating here magnitude, so we need to take it positive. And this would be the final answer. E is equal to 6 into 10 to the power 4 volt. And the key formula used in this question is E equal to m into del I by del t. So these are the questions now. In this part we discussed finding energy of a solenoid, finding mutual inductance of two coils, how they are connected. In the next part we will discuss basic application involved in the electromagnetic inductions like transformer, induction coil, induction stop, and basic characteristics of this transformer. So stay tuned.